Yeah. Respected INS members and friends, I once again welcome you all to this today's webinar, which is 22nd in the series. Your webinar subcommittee is actively involved in organizing this webinar fortnightly. We have invited eminent speakers from DAE and outside DAE to deliver talk on recent developments and challenges in varied topics and subjects of interest for our INS members. We have covered front-end, middle, and the back-end technologies of DAE program. We have covered on climate change, societal benefits, nuclear science, related health benefits, universe and its dynamics, etc., etc. Most of these talks have been popular talks for the benefit of the members. And today we have with us Dr. RN Patra, who is going to talk on rare earth industry in India, prospects and challenges. I am sure we'll all realize how important is IRE today, more than ever. On behalf of INS and on behalf of webinar subcommittee, I welcome you, sir, to our webinar series. We are fortunate to hear from you the prospects and challenges of IRE. IRE is a mini Ratna category A company, and it was founded in 1950, and it is jointly owned by Government of India and Government of Travancore, Kochi. Primary intention was to take up the commercial scale processing of monazite sand for recovering of thorium. Now it is producing more than 10 rare earth products, maybe more. Dr. Patra would tell us. So this year, IRE has achieved highest ever sales turnover and profit before tax sale since its inception. It is rated as excellent MOU secure company for 4 consecutive years. This is despite the pandemic and disruption in supply chain. So it is heartening to listen to Sri Patra. So before I invite him, I request our President, Sri S.K. Mehta, to give his opening remark, please.
Thank you, Dr. Ramarao. Let me welcome Dr. Patra. At the same time, let me welcome R.K. Garg, who was also the chairman of IRE. It is his initiative that he suggested Dr. Patra for this particular webinar. I'm happy that he has agreed to give this webinar talk. India is bestowed with a lot of natural resources, and every place the resources have got a different problem and different techniques are to be adopted. And IRE had done a wonderful job in that from the exploitation this. It is perhaps a very rare opportunity that we hear from IRE, the kind of development they have done. And I think I welcome Dr. Patra and look forward to his talk. Thank you.
So thank you, sir. Thank you, Dr.
Now, may I request Dr. Ramanamurthy to introduce Dr. Patra to the audience, please?
Good afternoon, and it's my. Am I audible?
Yeah.
Yes, sir. Yes,
Yeah.
sir.
It's my privilege to introduce Dr. Patra to this forum. Dr. RN Patra was former chairman and managing director, Indian Rare Earth Limited, Mumbai, and the former president and honorary member of the Indian Institutes of Metals, Kolkata. Dr. Patra joined BARC in 1977 after graduation in chemical engineering from IIT Kharagpur. He obtained his PhD from IIT Mumbai in 1988 on research and development of processes related to reverse osmosis and desalination of brackish and seawater by using membranes. His contributions at BARC include the design, installation, and commissioning of technology demonstration plants for recycle of industrial waste in RCF, Trombay, and brackish water desalination plants in rural areas. He was associated with the corresponding technology transfers as well to the industries and also holds patents in related fields. He joined IREL in 1989 as manager of the synthetic rutile plant of its OSCOM unit. He served as the factory manager of thorium plant Trombay, which was subsequently decommissioned in 2000. He thereafter served in corporate marketing and technical departments of IREL before being elevated to the post of Director Technical and CMD of the company. He superannuated in 2015. He has wide-ranging experience in aspects such as compliance with environmental clearances, pollution control norms of mining and minerals, both in domestic and international markets, negotiations with multinational companies for finalizing long-term sales agreements, and labor unions for long-term wage settlement. Am I audible?
Yeah, yes. You
Sir,
are.
yes.
Sorry, because some other screen has popped up.
Yeah, I don't know from where it is coming.
Okay. Sorry, I'll just repeat that sentence. For finalizing long-term sales agreement and labor unions for long-term wage settlement, corporate governance, execution of projects under corporate social responsibilities program, compliance with company law and management of company boards, etc. He has participated in numerous national and international seminars as invited speaker and lead organizer to share his knowledge and experience. He is currently a non-official director of the Board of Fertilizers and Chemicals, Travancore, chairman of the committee constituted by Niti Aayog to establish rare earth value chains in India, advisor on heavy mineral beach sands to Andhra Pradesh Mineral Development Corporation, and an external process safety expert of UCIL Jadugra. He is a member on the research councils of CSIR as well as their laboratories such as NCL, NML, Jamshedpur, and Institute of Minerals and Materials Technology, Bhubaneswar. He also serves as a consultant to several private industries in the metallurgical and mineral products sectors. So with this introduction, without further ado, it is my honor and privilege to invite Dr. Patra to kindly commence his presentation on rare earth industry evolution, Indian prospects and challenges. Over to you, Dr. Patra.
Thank you, sir. Just give me a time, sir, to upload the slides.
Yeah,
Sure.
yeah, please, go ahead.
Sir, is it visible?
Yeah, you can make a slideshow.
Yeah. Now, is it okay?
Yes.
Yeah. So at the outset, let me thank Sri S.K. Mehtaji for giving me this unique opportunity delivering this webinar. This has brought me to a distant meeting with my seniors, colleagues, friends, among whom I can see Garg Saab, who was my guru and basically, who brought me to IRE. In fact, he picked me up from the campus interview. And that's how I landed here. Now, let me start with the presentations. So this particular section, there are 3 sections in this presentation. This one is the introductory one. The rare earths obviously will be well known to this particular community, but just as a sake of a memory refresher, I would quickly go through it. Now, here the rare earths are. Rare earths today, as we know, are by the definition of International Union Pure and Applied Chemistry, Group 3 of the modern periodic table. And we have atomic number 21, that is scandium, 39 is yttrium, and then 57 to 71, lanthanum to lutetium. Now, there are total 17, but actually 16 are available on Earth. The number 61 is promethium, which doesn't have any stable isotope, so we don't get to see it. It is only detected through the spent fuels of atomic reactors or through the spectral signature of the distant stars. Now, rare earths, as the history goes, earths are according to the ancient Greeks, which are not destroyed by fire. The properties which are retained even after the fire test, that are earths. And rare, it was told, because in those days, even that those days means still middle of 20th century, 1950. The analytical techniques available were not good enough to easily detect these materials. Even titanium, zirconium, hafnium were also considered rare earths. That's the reason how Indian rare earth has its name, which was incorporated in 1950. Now, rare earths, about the 17, if you look at the crustal abundance of the earth, they are not rare, because cerium, the most abundant, is more abundant than nickel and copper, and we don't call them rare earths. Similarly, neodymium, yttrium, lanthanum, they're more abundant than cobalt and lead. Promethium, samarium, gadolinium, dysprosium, erbium, much more than tin on the Earth's crust. Mercury and gold, they are rarer compared to other set of rare earths. Now, what makes them rare is the concentration in which they are available on the Earth's crust to facilitate or to make feasible economic scale of mining is very rare. All over the world, there are about 300 such geological deposits which are currently economically favorable for mining. The reason is the geochemistry of rare earths don't support their association with common rock forming elements. Common rock forming elements are silicon, calcium, magnesium, and rare earths don't easily make association. And they are soluble in acidic media. So the hydrothermal fluids and in acidic pH will dissolve rare earth and take it away from its place of origin, except certain circumstances which we'll see subsequently. Now, for make our presentation clear, 17 conventionally are categorized under two heads, light rare earths and heavy rare earths. Now, they are nothing to do with their weight. As you can see, light rare earths are lanthanum, cerium, praseodymium, neodymium, up to promethium. Promethium is not available, no stable isotope. And you can see lanthanum, their density goes in increasing order with atomic number, 6.15 to 7.26. The rest are classified as heavy rare earth, even scandium, yttrium. Now, even though they're called heavy, you can see scandium density is 2.98, yttrium 4.47, less than those of LRE. Then why do we call them heavy and why light? This is again convention and history. This is what it is. In the earlier days, rare earth used to be identified by a multiple fractionation and dissolution. And you can see the lanthanum, cerium, praseodymium, and neodymium, they precipitate at the highest pH. This table itself is explanatory. All the rest, they precipitate at much lower pH or earlier than these four. Now the heavier ones will settle fast, and that is how the convention stuck, heavy rare earths and light rare earths. And light rare earths are named as cerics in industry parlance because cerium is the most abundant element among them, and that is how we call them cerics, the group, light rare earth. The heavy rare earths are represented by yttrium, the most abundant in them, and that's why some people call it as yttrics. So this is what we will be using quite frequently during the course of our presentation. Now come here, the chemistry part, the atomic radii part. You can very clearly see lanthanum, cerium has got much smaller, much higher atomic radius compared to the heavy ones. And here, sir. Can I continue?
Yeah, please, please.
Yeah. So here you can see the difference of the atomic radii. Yttrium, there is a difference. Cerium got multiple valency 3 and 4. Europium has got multiple valency 2 and 3. So cerium 3 and cerium 4 and europium 2, they don't fall in this line. And these properties decide how they can precipitate from their solution. And this is what is used in the entire rare earth refining chemistry. You can say scandium is not available on this map because it goes beyond this. This has got a radii somewhere around 8, much below the lowest of the scale. Now the importance in national security. Now national security, when we talk of two things comes to picture. One is the economy of the country and other is the defense. I mean the external aggression to protect the country from that. Now economy is important because growth is necessary. Population grows normally. So if economy is not well defended, there will be civil unrest. And the external aggression part is very well understood. And rare earths, they need fiber optics, erbium, lasers, europium, neodymium, terbium, host of them, precision guided missiles, high efficiency electric motors, guidance and control system. That's how it is. Now the entire rare earth market estimated in 2021 is around 5.3 billion US dollar, much less. Global economy 88 trillion US dollar. Even Indian economy is 3 trillion US dollar. But point is this 5.3 US dollar worth of rare earth market supports 2,000 times more in terms of their end use products. We will see subsequently what they are. They're starting from television to your mobile phones, display screens, energy efficient motors, and so on and so forth. Now, world production of rare earth was 0.28 million tons, that is 280,000 tons last year, 2021. And we have given a comparison compared to 1900 million tons of steel that the world produced, 68 million tons of aluminium, 26 million tons of copper, and so on. So you can see in the thing. So it is very minuscule, both in terms of value and in terms of production. But if you look at its economic leverage, it is about 2,000 times more. That is how they make the impact. Now, looking at the Indian rare earth market, data are taken all from USGS, United States Geological Survey website for ease of comparison. Now, the production was 2,900 ton rare earth oxide, both mixed and separated. Now, catalyst, polishing compound, ceramic colors based on rare earth are produced in limited extent in this country. We know the private entrepreneurs who do this, and they are good. They have been importing materials. I hope they must be taking it from the local production now. Now, rare earths, metal and alloys for metallurgical industries along with CFL, phosphorus, LEDs are all imported, whatever we see here. Electronics chips, most of the energy efficient drives having rare earth permanent magnet used in white goods. White goods are refrigerator, air conditioner, washing machines. Electric vehicles are imported in part. I mean, this audience may be aware that 30 to 35% of the component of our household washing machines, air conditioner, refrigerators are imported. These are basically these drives containing these rare earth motors. And today we see variable drives which are very energy efficient. They invariably contain these rare earth motors. Now, market of electric motors, smartphones, white goods in this country, I have put a thing number, 56.5 billion, 38 billion, and you can see this. This is a huge market, and 35% is imported. Now, this compounded aggregate growth rate of electric vehicle is 97% year over year. Last 2 years data, 3 years. Mobile phones 27%, rest is 11%. So there is a huge growth potential of this particular thing. Now, here is the application segment of rare earth in the industry. You can see the volume-wide segment is on the left side. That is the catalyst, is the luminous. Metallurgy, if you see, that is use of rare earth metals in ferrous, non-ferrous industries, and magnet, permanent magnet. Rare earth magnets are the most energy dense, and batteries, that is nickel metal hydride batteries. These three together, battery, metallurgy, and magnets, that is about 46% are metals. 54% are consumed as non-metal, either as oxide or as some other chemicals. Now, in value, and if you look at the magnet, most important sector, the applications are in acoustic transducer, hard disk drive, wind turbines, air conditioner, washing machines, electric vehicles, robotics, drones, and you can imagine any transportation system, and it is bound to have some of these. Now, the challenges here is there are about 16 we have seen, but only 10 contribute to 95% of all industrial uses. We have listed them here: cerium, lanthanum, neodymium, praseodymium, samarium, europium, gadolinium, yttrium, dysprosium, and terbium. These are mostly in the catalyst sector or in the magnet sector or phosphor sector, energy efficient lighting, and so forth. Today, in last 5 years, 4 elements, these are called magnetic rare earths: neodymium, praseodymium, dysprosium, and terbium. These four contributes to 91% value terms of the total basket of rare earth value. And more than 2/3 production of rare earth, volume-wise, cerium, lanthanum, and they are in surplus. We are yet to find a good consumption industrial market for this. This itself is a challenge. If you produce for these four, magnetic four, you have to deal with these two, cerium and lanthanum, 68% material. Now coming to the second section of our presentation, we will see what are the rare earth bearing minerals and what is the geology and mining and mineral separation. Looking at the rare earth bearing minerals, they can be classified. There are about 200 and odd these minerals. But we can classify them under four major heads: oxides as carbonates and phosphates and silicates. Now, simple minerals are those which chemically will be either oxide or carbonate or phosphate or silicate. Complex mineral will be a mixture of one or the other. It could be a mixture of oxide or carbonate or phosphate. And these complex minerals will be very difficult to process. Simple minerals are easy to attack industrially and commercially. Now, basnasite and monazite, they are the richest source of LRE today and cater to almost 100% of rare earth production globally. Genotime and ion adsorption clays, which are weathered apatite and genotime concentrate, they are the main source of HRE, that is heavy rare earth. Phosphate rocks, old fly ashes, bauxite residues, that is red mud. They are also becoming target source for rare earth as the industry demand is growing. Now, recovery from RE electronic waste is quite promising. Yeah, our country also has brought in a lot of legislation, and there are about 10 private entrepreneurs in Delhi and Bangalore and Hyderabad, which has come up to cater to this particular requirement. Scandium recovered from titanium slag. Even it is said that scandium is available in Orissa ilmenite, and the sulfuric acid pigment producers in China, they were targeting to recover it. Even one Indian entrepreneur who set up a plant and operating it near Chhatrapur, Orissa, he has filed for a industrial permission for scandium recovery from his proposed titanium pigment plant in Oscom. Now we are coming to the first one, the heavy rare earth source, the ion adsorption clay. They are basically clays, and we know clays are good to absorb or exchange ion easily. They are ion exchange media. Now rare earths are contained in this clay in a very loose form. And as you can see, geologically, the clay is the topmost portion of the Earth's crust. It is the magnetic rocks which get degraded or detrited, forming the soil, and because of the plants and vegetation growth. And the rare earths get released because of that, because of the acidic conditions, because the vegetation creates a humic acid, organic acid, and that dissolves this rare earth, and the clays retain them. So for these deposits, three things are important. It has to be a moderate to temperate weather, so that there is a temperature in the warm zone, and then this vegetation should be there and clays should be there. If these three things are there and rare earth deposit is available in the granite substrate and the particular composition of granite so that they are easily leachable, you get this kind of deposit. And southern China has plenty of them, and they cater to today about 70% of world's deposit. Last 5 years, Myanmar, the deposits have catered to the balance 30%. Otherwise, these are the most sought after thing in the whole rare earth industry. Now coming to our favorite monazite in this country. Monazite geologically occurs from the magmatic rocks, volcanic eruptions, and this is how it comes to the magma or the solidified volcanic rocks. And again, the weathering action, the wind action, the continuous temperature fluctuations that causes crack, and the vegetation that will make the rock break. And these are hard minerals which will get released. The water action and the wind action will carry it to the sea through the system of rivers, and the sea waves accompanied by the sea waves will throw the lighter sands out from the heavier minerals and they get deposited. Over geological timescale of millions of years, the sea line or the water line might have receded or might have undergone fluctuation, exposing the land shoreline, and that is where they get deposited. And because this deposit and this formation is repeated over thousands and millions of years, it is very normal to see thick deposits of these dark heavy minerals interlayered with a deposit of sand also. Now we'll see how they look. This is how they look. In the left is the placer deposit in Kerala, Malabar coast, where the sea waves will carry the dark sand, put it on the beach in the monsoon, and post-monsoon they will be harvested. And this is a continuous process, ad infinitum. It has been going on for 100 years and it continues. Dunal deposit on the east side, what I just said, the dark bands you can see and the lighter sand, they get deposited, and these are in the land side. And this used to be geologically underwater millions of years back, and today we are mining it. And these are the company operations all in the coast, headquarters in Bombay, IRL India, and we all know this. Now coming to the Indian rare earth resources. This has been taken up from a book by Rare Earth Element Resources by Jamuna Singh, 2020. He is the retired scientist from AMD. Excellent book on the rare earth resource, Geology. And you can see all over India now rare earths, because starting from, I would say, the 12th plan, so that is, which ended in 2017, 31st March, there has been extensive exploration of rare earths all over the country. And the result is today we have all kind of deposits, starting from bits and placer to carbonatites and mixed kind of minerals in the western side also. Now, this is a snapshot of the bits and heavy minerals. We see 5 major bits and heavy minerals which are listed here. The phos-3, ilmenite, leucoxene, rutile, they are titanium bearing. Zircon is zirconium bearing. Monazite is the thorium rare earth phosphate. Sillimanite is aluminum silicate. Garnet is iron aluminum silicate. Now, in addition to this, on the Malabar coast, we see something called stearolites. They are in very minor quantities. They are basically hydrated iron silicates, iron aluminum silicates. Stearolite means cross, and they look dark, and many times they report on the sillimanite product. So diamond, we don't see it here, but we see in the beaches of Orange River mouth, Namibia and South Africa border. So Rio Tinto has got the very big diamond mines there. And along with diamond, we see all these heavy minerals there. So heavy mineral definition is those which are density more than 2.9. That is the sand. Now coming to the separation. What you do is the digging of the sand, as my previous boss, the late Sri Kumar Banerjee, Chairman Atomic Energy, would often say, this company makes money by selling sand. You basically dig sand from the seashore and then you push it through heavy upgradation plant, then mineral separation plant. Now, in the previous slide, we have indicated the various properties, that is magnetic and electrical. Now, ilmenite, rutile are conducting, and among them, ilmenite is magnetic, rutile is non-magnetic. Garnet, monazite, zircon, sillimanite, they are non-conducting. Among them, garnet is magnetic more than monazite. Monazite also is magnetic, but the least magnetic. Zircon, sillimanite, absolutely non-magnetic and non-conducting. So this is how the scheme, and you get 5 products. Ilmenite, rutile, 6 products. Ilmenite, rutile, garnet, monazite, zircon, and sillimanite. Now, when you get these products, we have classified these products in terms of their market impact. The yellow ones are commercial, ilmenite, rutile, garnet, sillimanite. The green one, strategic, because it has thorium, uranium, this is a source material. The zircon, part commercial and part used in atomic energy. Now we come to the last part of the presentation. This is the rare earth industry evolution, dynamics of this industry, and how they become critical. Now, brief history, they have taken 150 years for their discovery due to the difficulty in analytical systems. It started 1750, ended in 1947. Because actually the last one was promethium. Invention was just before World War II, 44 or 45. But the announcement was delayed owing to World War. So the announcement was made 47, the year India got independence. And 1884 was the first application of these rare earths. The application per se was not for rare earth in a big way, but for thorium, gas mantle. And 1% cerium nitrate was added in the gas mantle to get the bright light. And the invention was in Europe, Austria. And this is what is the gas mantle. And the gas mantle renders 10x brightness compared to the old bare glass gas flames. So during early 20th century, the mantles were competing with electrical bulbs. Thomas Alva Edison was trying to place his electric bulb against these particular mantles. That is the reason electric switches are all placed in one place, because gas valves are all put in one line. So thorium gas mantle from Brazilian monazite was stopped to the European processors and American users somewhere in 1903 due to geopolitical reasons. And that is the reason where when the traders started seeking alternate source and landed in Malabar coast 1909. So the mine what IRE operates in Kerala and Manavala Kurchi, they are more than 100 years old and started by the Britishers and the Germans. Subsequently, these mantles have been replaced by zirconia and yttrium oxide because thorium was radioactive. So it has gone to a non-radioactive source, but with a penalty of the brightness. And today mantles are least sought after because LED lights are ubiquitous and you can easily have a battery operated or solar panel aided LED light to any place. Otherwise it was camper's delight. Now, subsequent to these mantles, we see these industrial applications. First was the metals. Inventor of mantle invented this simple fundamental process, graphite crucible, take anhydrous rare earth chloride, electrolyze them, and you get the mist metal. And these mist metals were used to get what you call the flint stone, or the metal that causes spark when hit hard or when rubbed. This was a big craze in terms of lighter, gas lighters. And that is how the inventors made his money. And within 10 years, he came out with another invention. That is mixed rare earth fluoride when used as a core in the carbon electrode will render very bright light. Before that, it was all lime light. That is a acetylene torch impinging on a lime block, which will give you very bright light. And that is what will be used in opera shows or in public display. That term limelight comes. But this made a big change, that this could make it portable, very small and easy to use with electricity, of course. Those days, limelight, no electricity. Here it was electricity available 1910. And these are all cinemascope projections. You can see this. And this was used in First World War surveillance of prisons, the lights that is needed. Some old English movies, you can see this. Rare earths were produced in excess as industry demand was thorium in gas mantle. Those days also, this was the problem. Thorium was used and rare earth was dumped. Incidentally, India also faced the same thing. We had first this gas mantle plant in thorium plant Trombe. Till 1960, these rare earths was dumped in the sea, Arabian Sea. That's what I was told. Those days, of course, there was no regulation, no pollution control or IERB. But onwards, the market started picking up. We will see this how. Now comes atomic energy, 1939. The first fission and all those was invented, and the world came to know about the monstrous power of this particular invention in 45, those two explosions. And atomic energy, when the fission happens, you get these rare earths as the fissile fission products. And this is a poison, neutron poison. So this needs to be removed from the spent fuel. And that is how the process of solvent extraction, ion exchange were developed in 1940s. Solvent extraction followed in 50s. And we used a solvent extraction system in thorium plant in a very small scale in 70s. The thorium plant was based on fractional precipitation and dissolution principle, the first principle. And subsequently, this solvent extraction, because of the ease of operation, took over and replaced it. Atomic energy, the rare earths are used as control rods. Gadolinium, europium, and samarium control the reaction. And zircon is used in the cladding of the fuel cladding. And some of these atomic reactors, the thermal reactors, they are supposed to be the chief source of thermal energy for generating hydrogen, the green energy, which is being talked about. And zircon is necessary for the fuel cells, solid oxide fuel cells. And that is how the significance of these from the atomic energy perspective point of view. Coming to the applications in the catalyst, we can see prior to 1960s, the petroleum refining was not that efficient in terms of gasoline yield. When rare earths came, the geolites started using this. Earlier, geolites were used without rare earths, but they used to delaminate. The alumina will soon lose its exchange capacity and it will require frequent changing. With the use of mixed rare earths, geolite catalyst, the entire scenario changed. And that is how rare earth market boomed from 1960 onwards. That is the catalyst application. Now, if you look at it, here is the break, because till 1980 middle, we are all using mixed rare earths, permanent magnets, metallurgical, ferrous, non-ferrous. These are permanent magnets of very low energy density, ceramics, optical glass, even farming. China was desperately trying to push their use in 80s by persuading farmers to use this. Nuclear, pharmaceutical, battery, hydrogen storage, cryogenics, no use of mixed rare earths. It is only after separation becomes easily available, these usage got developed. Now here is the application of phosphorus. 1962 things happened. One is use of catalyst in the petroleum refining. Second is color television has made an impact, and europium was the phosphor there. Molecular mine opened because it has the highest europium content to make the entire operation economically feasible. How the industry flourished with a new application, phosphor application. But over the years, the technology developed, the phosphor technology also underwent a change from tri-band phosphor, which you will use red, green, and blue, three types of different phosphor. The simplification happened that you have one phosphor material as a coating, and you have a light that causes a yellow emitting wavelength. So the blue light, when it hits the phosphor coating, will give the white light. This is what is the LED mechanism. And with this, the market for europium completely diminished. Today, europium in last 5 years or 10 years is not having that significance what it used to have in 1960s for the molecular mine. Now, subsequently, we have cerium oxide usage in a novel use. Today, cerium oxide is used to polish solar photovoltaic cells and to polish also these IC chips. Earlier, it was used for polishing glass. Today, nobody needs glass polishing because float glass comes with absolute good finish. Don't require any polishing. And the television screens, everything has undergone a change. From the earlier CRT TV, we have LCD LEDs, we don't require any polishing. But a new market has opened and that use pure cerium oxide in a different fashion. Now, here is the permanent magnet history. It starts with our earlier making mismetal by that simple process of electrolyzing anhydrous rare earth chloride. When they used to do electrolysis, they will ultimately end up with a lot of dark sludge, and that was all piled up by the Japanese producers, American processors. They found out that this is nothing but cerium, samarium, and ytterbium mix. Europium was much less. Samarium, ytterbium was in good quantity. So this was that. They don't reduce easily in the electrolysis system. Now they have to find a use for the samarium, and that 1960s samarium cobalt SMCO5 magnet was developed by Jet Propulsion Lab in USA. And one has to wait another 10-15 years till cobalt became expensive because of civil unrest in Congo, because Congo, Democratic Republic Congo is the main supplier of cobalt. Even today, more than 50% cobalt comes from there. So because of that, cobalt becomes so expensive, the innovation and that search for alternate magnet landed SM2CO17, which not only reduces the proportion of cobalt in this, but also results in a much better magnetic property. These magnets retain their magnetic properties at much higher temperature, and they have much lower temperature coefficient in terms of diminishing coercivity. Now, 1984, we got neodymium iron boron magnet, and this invention happened on both sides of the Pacific, in Japan and as well as in USA, same time. So that obviously led to a lot of patent related disputes, but subsequently it got settled down and the world benefited out of this great invention. Now the battery, nickel metal hydride batteries are made in 1989. And these are the first batteries which found use in hybrid cars. But subsequently they are losing their market to lithium ion batteries, which are much better and cheaper to construct. But these batteries do possess some unique properties. For example, operational capability at low temperature and retaining the charge longer when idle. Now the last one is the lithium nickel, the battery electrode material or the metal, which is known as NIMH, nickel metal hydride, is also a hydrogen absorber. Now, hydrogen, as we all know, is very difficult to put it in a liquid form, and it goes to very low temperature, near absolute zero temperature. So these materials, they make hydrogen storage easy at a low pressure, and that is, and the volumetric density of hydrogen improves. That is how is the importance of these materials. But there are many alternatives to this today. So they also are not unique that way. Now this is what is the global production. Now you can see earlier it started in the United States of America or Europe producing these rare earths. India was there that time, 1950s, we had our own industry. Slowly it all started waning and China took over. And Chinese resurgence happened from mid-80s and went high, and we'll see how the trajectory happened. China's R&D effort started in 1975, and it was all their government support and push to develop this particular technology. China, in fact, tremendously leveraged the WTO mechanism where economic sourcing of material was given priority by all Western processors. And that is how China became a factory of the whole world. The Chinese system of doing this infrastructure and giving support to the industry is unique. There are many small entrepreneurs who only focus on production. The two ends, marketing and sourcing of materials, are done by state-owned companies in those days, in 80s and 90s. Today, of course, they are all big conglomerates. They have taken the business from the whole world, and they are all consolidating and becoming huge mega enterprises. But initially they started like this. The mechanism was this, completely supported by the state. Now, this is the scenario 1955 to 65. You have 5,000 ton production average, become 20,000 ton. in the next thing because of petroleum refinery usage and phosphor usage. 75 to 85, your magnet usage starting and other technical usage picking up. 85 to 95, mostly magnet driven, NDFEB, catalyst, and so on and so forth. Industry is growing. Now in 2010, China's share of mine production was 97.5%. Everybody closed business. India also, we stopped in 2004. Malikat mine stopped production in 1993. Europe, all processors, they started getting cheap materials from China. And that is how the 2011 Chinese embargo created a worldwide alarm bell. Everybody was, searching for alternatives or trying to develop alternate sources. Now the criticality today is different. What was in 2010 is different in 8 years' time. Now, as you can see from this infographic, 2010, 97 or 95% rare earth China production mined. 18, it is 70%. In terms of mixed rare earth concentrate, 95% that time was China. 8 years later, it was 70%. Mostly because Lynas has come, Australian company, taking material from Australia, processing it in Malaysia. Then separated oxides, 90% from China, 85% in the rest of all, that is Lynas because of that. Metal, 80% and then 90%. 80% metal was being made in China those days. The balance 20% something in Europe, America. They all closed today. 90% metal is made in China. Alloy 85% was that time. Now that this, you can see there is a trend. The basic commodity of rare earth has come down in China, but the value added products have gone up from 80, 85, 80 to 90%. Even China today produces more than 94% or more than 90% of permanent magnets, blanks. There are only 2-3 producers in the Europe and America side. So China controls 72% of world solar module manufacturing and 45% of lithium ion batteries. So this is another problem because wherever you use motor, you will be likely to use either lithium ion batteries or there will be some renewable energy generating system in terms of solar module or wind turbine. Now coming to the Indian rare earth economic value chain, the box which is shown in green, we have now, starting from mineral exploration to mining, separation, extraction and refining. Metals alloys and the magnet making don't exist. The component assembly, partly it is done here. And there is a huge market, as we have seen in the beginning slide, for the ultimate goods, equipment and consumer durables. So this in snapshot is a scrap metal recycling for entire elements or metals in the periodic table. The blue ones are the most recycled. You can see the most recycled ones are copper, iron, lead, and the PGM, the platinum group of metals. That is gold, platinum, palladium, so on and so forth. Rare earth and all these recycling rate is shown to be very less. That may be because it is just an nascent industry application that is growing. So over the period, as the industry matures, this recycle has to pick up because rare earth manufacturing itself has got the recycling inbuilt in that. So technology obsolescence is a big problem in recycling rare earth based products because whatever composition or components you see 10 years back is no more the same now. A simple example, 1978, Sony introduced Walkman. Those who have 78 Walkman models of Sony will get samarium cobalt magnet in that. But subsequent versions of Sony Walkman will not have samarium cobalt. 10 years or 15 years later model are likely to have cheaper neodymium iron boron magnet. So now somebody has to do recycle, he should have these knowledge, which year, which manufacturer, and what would be the composition. Then only he can easily segregate it. That's a very practical problem for industrial scale recycling of these products. But then blockchain, artificial intelligence and digitization is helping the present recyclers in a big way in this particular field. Now we'll look at the permanent magnet industry in our country. Now the demand drivers, now why it is important, first is the geopolitics, resource nationalism. Now every country wants to stick on to his own natural resources or use it as a bargain for getting his need or further requirements. One example we can see today, after Ukraine war, even Australia, a country which has always dealt with commodities and never had any value addition industry in their own land, is now seriously thinking of industrial value chains. Iluka Resources is setting up a very big monazite processing plant, going up to refined rare earth products there at $1.2 million US investment. That's only one, but then there are many other companies who are even hydrogen production in a big scale for export to Japan. They are all being seriously considered. Even Australia government itself is seriously thinking of defense manufacturing and starting their reinforcing their defense system. So self-dependence is another issue that has come very much after COVID-19 pandemic. That is resilience and supply chain agility. How quickly you can move to alternate supply source so that your economy is dependent. And how quickly you can recover from the shock. Now, energy, technology, and market, these three are the biggest bargaining issues. Technology for these are not available easily. This is held by a handful of multinational companies. Market is plenty. Like India, our own country is a very big market for this. Materials are located, naturally distributed in few geological regions. So that is how the geopolitics takes shape. Now, climate change concerns, every country has become declared his own intended goals to reduce carbon. Our country is committed by 2070, I think, to become zero carbon. Europe 2030, some countries 2050, and so on and so forth. They all need these particular materials and new energy systems. It is very interesting to look at some of the salient features. Rare earth permanent magnets are a generic products per se, but you can see this on the right hand side. They come in various shapes and sizes. So unless you know the end consumer's requirement, it's difficult for you to set up a commercial scale manufacturing unit. During early phase of rare earth permanent, it was all powder metallurgy technique, but subsequently the technique has changed, and it has resulted in a lot of saving in terms of materials and in terms of use of some heavy rare earths which are very scarce. So when you don't know the end customer, you will make some standard blocks and the end customer will machine it. And that will result in a lot of scrap wastage or swap, what we call machine waste. This can be as high as 125%, even more, based on the size. For a smaller size component that goes in final assembly, the waste will be high. For a bigger size component, waste will be less. Current practice is enhanced integration of manufacturing. This is because of this, manufacturing is getting integrated with production. That is, if you need a particular shape or a complex shape, then you formulate a particular material composition and work for that and set up your manufacturing line based on that. So most of the patents in this magnet of late are all on manufacturing, the magnet formulation. Now, what has happened is the expensive the neodymium, praseodymium are getting replaced by cerium and lanthanum, partly due to improved metallurgy and process manufacturing techniques. And lastly, RE metal and alloy production are distinctly technologically different for our processes, but in practice, they are very closely integrated for one simple reason. Rare earth metal is highly oxygen prone. It can take oxygen from atmosphere, whatever nice packing you do, whatever precaution you do. And once it picks up oxygen, oxygen is a poison for magnet. More than 500 ppm, the less is the oxygen in the magnet that you produce, the better is the magnetic properties in terms of remanence and coercivity. So no magnet producer will ever stock metal. He will always stock oxide. and convert to metal just before he makes magnet out of that. This is one simple, very important thing to bear in mind. And that's the reason rare earth oxides world over today are priced based on their metal contents. 1.17 ton of rare earth oxide will give you 1 ton of metal. If you look at the price chart today, RE metal and REO, you will see metal will be 1.17 times the REO price. India REPM industry, this country has got very good manufacturing base of ferrite and alnico magnets. Dozen private enterprise around dozen I know today, there may be more. Information is about 3 years old. So they get blanks and they machine it to the end user's requirement. They give corrosion protective coating and they supply. The swarf generated from these fellows are collected by scrap agents and sent overseas. And they were paying very nominal price for this particular waste. Now, if you have a metal system integrated with your magnet, in-house you can recycle this particular machining waste. And to that extent, your reliance on fresh material will be less. A few, 1 or 2, at least I know, who have 30 years of supply chain relationship with the Chinese, they have set up a complete magnet manufacturing system, starting from alloys and this rare earth metal which they get from China. Now, last 2-3 years, I see that a few agencies that come up in Bangalore and Hyderabad who give these design services for machine design, electromagnetic machines, using finite element analysis of magnetic flux coupling of the system because of the electric vehicle and other things. So the ecosystem is developing very rapidly and very well in this country. Now, what government initiatives are being taken is atomic energy, defense, and CSR. I think they have all taken up programs to develop metals, alloys, and permanent magnets based on the state-of-the-art technology, whatever is not available from overseas. Government of India has taken a series of steps to make India competitive in manufacturing things globally. There are many of them. I have listed some of them: multimodal transportation, infrastructure, roadways, rationalization of tax, single window system, and so on and so forth. Even production link incentives are being given. So defense manufacturing, one of the biggest, which is expected to create a very conducive ecosystem for supporting this rare earth magnet in coming 5 years' time. Now, but the challenge will be again supply and demand gap management for the cerium, lanthanum, and all those products which do not have a market. Now, this slide I have brought in to show this problem. What we have seen in the previous is not unique to rare earth per se. I have listed raw steel, aluminium, ferrosilicon, magnesium, titanium, rare earth oxide, and zircon, all critical materials. Now, except raw steel and aluminium, India is in the red, which growth in last 10 years is in line with the global growth or competes with China. All others are very poorly lagging. Ferrosilicon, hardly any growth because they are energy intensive and nobody makes ferrosilicon in India today. Magnesium, we don't have any production. Titanium, very low, 500 ton. We have one in Kerala that still continues same. Zircon also, these are 19 data. I don't know what would have happened. And they're all taken from USGS, United States Geological Survey. Now, if you look at the interconnection, it is like this. The bauxite residue, which comes from aluminum industries, has gallium, vanadium, and scandium. Silica quartz will make silicon metal and ferrosilicon. Aluminum and silicon metal can go to dolomite to make magnesium metal. And incidentally, the same system gives you calcium metal. Calcium is reduced with aluminum to get calcium metal. We don't make any calcium metal in this. And calcium metal also is needed for rare earth metal manufacture. So the entire interconnection is shown in this. The red line shows which is used as the input material, and the blue line shows which goes as a finished product. So this issue is generic. It is not limited to rare earth per se so far as this country is concerned. Now we'll close the last one. The world today is intensely interconnected in terms of trade, people, finance, and data. Technology change is disrupting 10 times faster and 300 times the scale, roughly 3,000 times the impact. These are from some management study reports. Renewable energy products are used in renewable power, and we have all seen this. Now, most important is the new energy economy is going to be highly material intensive. So the country needs to have a strategy in place. A lot of things are happening and will continue to happen. And what will remain key is the last, close coordination between the academics, research development industry with government policy guiding them. Thank you.
Thank you, sir. It was an excellent talk. Many things we were not knowing. Great to know now. Now the session is open for discussion, and if there are any questions.
Yeah, Dr. Ramaro, can I ask something?
Yes, please go ahead.
Dr. Patra, it was a very comprehensive talk. You have not left anything untouched. It's a great pleasure to have heard you. I have one or two small questions.
Yes, sir.
Number one, as you have indicated, China is really dominating this scene actually. And I mean, India is way behind. Even those countries who were able to compete, they are also now backing out. But that is not the really ideal situation. People have to take up the challenges. Now we cannot say about the compulsion of other countries, but within our country, what I want to know is, you have indicated the important application is there between permanent magnets and perhaps in this computer disk, etc., and some of these our mobile phones. These are some of the high-end applications. Now the rare earths which we need for that, do we have sufficient supply within our own country? Basically, monazite is the source. So which are the elements, rare earths needed, and what is the availability of these rare earths within our country. Even if we try to catch up, do we need to have these resources available? That is number one. Secondly, what I was wondering that when we import some of the magnets, whether it is for turbine and other applications here, that recycling technology we should try to also focus on. So am I clear about these two questions?
Yeah, so the first one about your material availability. So far as the requirements of this particular country are concerned, because that is most important. That is space, defense, and atomic energy. We have all the wherewithal. The materials we have, the know-how we know, and in fact, BRC has been the giver of this particular technology to space and to
Panchandaji, he is giving a reply to you. Are you able to hear?
No, I missed some part of it actually. Okay, anyway, let me go
I'll
on.
repeat. Okay. Your first part of the question was about material availability.
Right.
For our self-sufficiency. So I was trying to tell that as the strategic requirements are concerned, defense, atomic energy, and space, we have not only the material, the technology, and we have all knowledge. In fact, atomic energy has been the forebearer in this, giving the material technology to space and to defense in 70s and 80s. But what has happened is these are all small requirements, small scale requirements. The method or the technology or the process that we adopted need to be refined or need to be developed further for catering to the large scale commercial requirement. That is what we lack today in terms of technology. Now, assuming that we produce all our material, starting from mining to metal and to alloy and to end things, we do have a lot of resources in this country which needs to be explored. Now, there are two challenges. They're all resources. What percentage of these resources will be available for exploitation, which we call reserve? That itself will require a lot of political support, because as we have seen, our entire monazite is in the coastal area, and coastal areas are thickly populated. Now, how you will get the land, and after mining, how you will return the land back to them, win the goodwill of the people. And the biggest competitor to you in this are the real estate people, which I realized during my service career. How you negotiate this challenge? These are all issues needs to be, discussed in some other forum and detail. But then the point remains is, yes, there is a possibility and it can be done. It is not impossible. Now, the second part, how to do it, whether we can get technology, nobody gives you technology and asking. Now, because of in a different way, I was seeing the Indian technology scenario, ecosystem, industrial ecosystem in developing in a different way than the West. The West invented, then outsourced the manufacturing to a cheaper country, and then moved on to service and bigger technology or science research. This is a market, unlimited market or very promising market. What we are doing today, we are integrating from the assembly side. Look at what is happening in lithium battery. The assembly part is being done here. The software is being developed here. And lithium cell manufacturing is one part, but putting cell into packs with a cooling system and a software is the second part. The second part is developing fast. The last part, that is the anode cathode, probably will take time and material will come last. It has not happened in the West, but in India it is happening. Look at magnet. We are starting from the low end side, getting blanks, machining, giving it today. And somebody with his Chinese supplier set up a very generation 1 technology, 1990s technology to make magnets in a very small way. But that's the beginning. And other research that is happening in the labs, they need to be translated. This is a mechanism which we should do. So during my private consulting, I found a very big bottleneck for a small private entrepreneur. Somebody wants to do some research technology on this. He needs access to sophisticated instrument, XRF, XRD, ICP. He cannot afford putting 10 crore creating a facility. And just putting money is not the end. You need very skilled operators to operate them, and their salary itself is high. So there should be a public system, either a government lab or some analytical system where he walks in, gives his sample, gets the result next day. The way we get our pathology reports. This is what is available in China. Anybody wanting to do anything, he can simply walk in and get his things tested and get a result. Here we don't have. This is the bottleneck. These two things, if you do, things will be very fast. That a translation mechanism from the government-owned research laboratory to the small-scale entrepreneurs, and a facility where a small-scale entrepreneur can go test his ideas, test his product, and come out with results.
I think that was an excellent reply. Thank you, sir. Any other question? We have somebody from IRE, General Manager. You have any question? You are Mr. Chandrasekhar, right?
Yeah, good evening, sir.
Yeah, please go ahead.
Namaskar, Chandrasekhar, how are you?
Fine, sir. It is really a privilege to hear our very own CMD, sir. Really, it's a privilege and a fantastic presentation. Really, a lot of information. And I have two queries here, which Sir can enlighten us. One is rare earth permanent magnet industry is a good potential for as a value chain for rare earths. And second thing is this catalytic converters. Now, the present situation is we don't have much manufacturers of permanent magnets in a big way in India, and also the other industry like catalytic converters and also wind turbines. Most of these industries are dependent on imports. Most of their critical components are imported. In that situation, these industries should develop before we get like a sufficient market for, like we should have more manufacturers of magnets so that there is a outgo for our rare earth products. What is your views on this, sir?
The industry is developing. Because if you see, I got in my first two slides, I've given a presentation. Windmill is growing at around 11% year over year. And it is estimated as some billion. I don't remember the number, but it is developing. What is happening is they are getting the rotor part and assembling it here. Yes, but not all windmill people use permanent magnet. Let me tell you this. This is a misnomer. People who use permanent magnet in windmill are the ones who build megawatt scale windmills, particularly for offshore applications. And where megawatt scale windmills will happen, where you get wind energy density high. India, if you look at the geographical location, our wind potential areas are very less compared to the solar areas. If you go above 30-35 degree latitude, your wind potential areas increase tremendously. China has them, entire Europe has them. In fact, there are windmills 12 megawatt, 13 megawatt, 15 megawatt, 3 megawatt may be median there, that side. In India, probably 750 kilowatt, less than 1 megawatt. Here you see wind farms. Here we are going only up to 100 meter height today. 120 meter renewable energy website is putting the potential estimate. Probably we aspire to reach 120 meter height to extract wind energy in another 2-3 years time. So the requirement of permanent magnet windmills in India is not that critical now. But point is, if there is a growth potential, Indian entrepreneurs are very smart to catch on to that, and they do it. Whether it's government or no government. It has happened in software, it has happened in electric vehicles, it has happened in lithium batteries, it is happening in rare earth magnet also.
Thank you, sir.
I have a small clarification to be made. One small clarification required, Dr. Patra. One gets the impression that the Chinese are producing a whole lot of rare earths and we are producing very little. However, the latter part of your talk shows that even if we produced rare earths in larger quantities, we will not be able to use because of that, anyway, we are importing the finished components to be assembled. Now, how does one get out of this cycle that because you do not have a market, you do not develop technology, and if you do not develop technology, you are not able to exploit the resources because you are looking at the wrong end of comparison of Chinese production and Indian production.
See, it is like this. Let us first define the objective. The objective is not to compete with Chinese. The objective is to make our country self-sufficient. That if tomorrow import from China stops, then we should not be left in the lurch. That's number one. And number two, if we reduce import and make manufacturing globally competitive, we will be able to export also. So if these two are the objectives, then we should look at the value chain analysis, which I presented. Today, the only two blocks which are missing are the metal and from metal to magnet making. And when I say magnet making, I mean the latest state-of-the-art technology. Otherwise, magnets are being made here. At least 1 or 2 people are doing it, but in a much smaller scale. And that technology is much older. So now the latest state-of-the-art technologies which are environmentally acceptable, suitable, and competing cost-wise, being developed by space research and atomic energy and defense and CSIR labs. Probably in 2-3 years' time, they should come out. But the question is, it should quickly find its way to the private entrepreneurs. That's the missing link. And if today you give support in way of analytical services, testing services, probably lot many entrepreneurs will come out much quicker. That is the point I made. Otherwise, people are doing it. People are getting magnets, machining, assembling. Yes, sir. Sanat Kumar.
Sanat Kumar.
Dr. Patra, I have 2 questions. Can you hear me?
Yes, sir.
Yeah. Go ahead.
Yeah. Okay. First question is, you were telling that the magnets are machined and there is a lot of wastage because of that. My question, because I really don't know, my question is, can it not be 3D printed or additive manufactured? Then you will get it the correct shape that you want and there will be 0 waste, according to me. Is that right?
You are talking of what just has happened world over, 3D printing of magnets. Making magnets by 3D printed, only one type of magnet can be produced by 3D printed as of now. These are known as what is known as isostatic magnets. That is having properties uniform on all sides. Otherwise, we make anisotropic magnets which are very strong. Anisotropic magnets are difficult to make 3D printing based on the current technology. But
you cannot remagnetize them. You cannot remagnetize to correct the correct orientation.
But what happens is magnetic property develops under in one axis, A, B, C, the 3 lattice of the crystal. You get the C axis developing magnetic properties, and these are anisotropic magnets. They are very strong. Isotropic magnets were the first invented in 1984 by that USA fellow John Crotes. And they are not that energy dense as this. These magnets are particularly used in resin bonding things, and they are good for 3D printing. People are doing it. Many complex shapes are being made. These ferrite magnets can be 3D printed also, and they are being used. In fact, instead of printing magnets, what is being done, the soft core of the rotor are being printed 3D. And that is resulting in new design of these motors, which are torque dense. That means you get a very high torque for a unit weight of these particular things, motor system.
Okay, I have another question, which is not really very technical. We keep reading in newspapers periodically that illegal export of rare earths is going on from Indian sands. Is it true or it is not true?
Well, sir, when I was in service, there was a problem, yes. And how there are cases also now pending in high courts and Supreme Court. And that has led government to cancel the leases and so on and so forth. And cases are going on. Now, after that, what has happened?
Any other? Dr. Garg? Dr. Garg has any question? Yeah, if there are no more questions, I think we will thank Dr. Patra for an excellent presentation. I think this presentation material are so good. Lot of things are to be understood in that. And I think once our YouTube is loaded, then I think we'll get a chance to do that again. And there are some 2 chat box we periodically here. Yeah, I think these are chat box put by Sanat Kumar that has already been answered. If there are no more questions, I will request our Secretary INS to give a vote of thanks.
Yeah, thank you, Dr. Ramarao. A wonderful, I think all will agree with me that Dr. Patra has delivered a wonderful webinar covering the various aspects of rare earths. Rare earths definitely are the future. We will be needing all these materials as we go for zero emission. We will be needing more and more rare earths. In fact, I was reading a paper in which there is a special mention that we will need extra energy and we will need extra materials to reach the levels of net zero emission. You know, as we move towards that with 2070 as the aim. So thank you very much, Dr. Patra. You made the evening very lively. So we thank you very much. And next, I thank our respected President, Shri S.K. Mehta ji, for guiding the INS team and the entire Executive Council of INS, and particularly the subcommittee for webinars, very ably headed by Dr. Ramarao. And I also thank our treasurer, Shri G.D. Mittal, and Dr. Shimjit Rajgopal of BARC for helping us in reaching the information about the webinar in a timely manner to a large number of people. I also thank all the members of INS and all other audiences who have joined. See, we can see a particular number as far as Zoom platform is concerned, but we really don't know how many of them were watching it on the YouTube, because we have the live streaming on the YouTube. And of course, in future also, constantly people keep on revisiting our webinars on the YouTube. So I thank all the audiences. And as I always do, if I have the information, I tell the audience about the next INS webinar. So our next INS webinar, probably 23rd. Am I right, Dr. Ramarao?
Yeah.
So next webinar, which will be the 23rd webinar, is scheduled on 2 weeks from now. So that is on June 18, 2022 at 5 p.m. same time. It will be delivered by Dr. Chandan Banerjee, who is the Deputy Director General of National Institute of Solar Energy. And naturally, by his designation or affiliation, you can guess what the topic is going to be. So yes, the topic is going to be solar energy in India, way forward. So looking forward to see all of you and many more people in our next webinar. I once again thank all of you, each one of you, and particularly Dr. Patra. Thank you and signing off.
Thank you.
Patra sir, thank you. Thank you very much for accepting our request and coming on screen to share your thoughts.
Pleasure.
Yeah, thank you, sir. Thank you very much. It was our pleasure too. Thank you.